Hello everyone and welcome. I'm Bijan Davari from IBM Research, speaking to you today from IBM Yorktown Heights Research Center in New York. I'll be talking about the future of computing systems and technology. And I'd like to start with this chart, which basically put it in the context that the confluence of the technologies with social, mobile, cloud, big data, and analytics are basically the main technologies that shape the future of the IT technology. And that starts with the amount of the data that is generated, which is increasing at an exponential pace. For example, the projections are that in 2013, the amount of generated data will be 4 zettabytes, and that is 4 times the amount of data that has been generated in year 2010, for example. That's a huge increase. And it's not just the data, it's basically the trends as far as the number of users, transactions, the computations. And in addition to that, there is a lowering of the barriers of entry, both with the advent of cloud as well as the various personal devices such as smartphones, tablets, and various mode of interactions of the sensors and the machines with the networking and the computing infrastructure. And if you think about it, there is not just a significant amount of increase in the amount of the data, but also the complexity of the data and also the way they are being consumed. So when you think about the complexity of the data, besides the volume, there is the variation, the modal variation of the data from speech, text, images, and so on, as well as the speed of the data, basically the reduction of the latency. And latency, you can define it by the amount of time that it takes to get the computing results from the time that you actually request a given computation. So that latency is shrinking very dramatically. And also there is a certain amount of uncertainty associated with the data that comes from actually where the data is being generated or to the place that it's modeled and so on. That's the veracity of the data. So when you add all of these things, there is an added degree of complexity from the data management as well as the various workloads and how you optimize a given system for those workloads. Now, one important point is that all of those things are being done at a much faster pace. So when you think about it, as far as the disruptions to the business model, the fact that the barrier of entry is significantly lowered with the cloud, as well as the generation of this amount of data, introduces new interesting business models. And the last mega trend that I'd like to mention is the contextual overload, where basically most of the data that is being generated now has spatiotemporal components where there is a location stamp on the data as well as the various contexts, and that also creates a significant expansion of the total amount of data that needs to be digested. So overall, the way to think about this is the big data is increasing dramatically and it has to be dealt with in a much, much shorter time. And in order to do that, we are moving from various phases of computing. So when you think about this, today we are at the programmable system era, where basically this model started around the 1940s, mid-1940s and up to today. And now what we are getting into, it's the beginning of the cognitive system era, which you basically have to go to a new computing model to deal with the amount of data that is generated. There is no way that all the data that is generated to be stored and acted on all of it. You have to make decisions based on the analytics, based on the insight that you're creating. You have to decide some of it to discard, some of it to store, and some of it to send to the next stage for further computation. And that's where I'm going to talk mainly throughout this discussion, that how do we get from the programmable system era to this cognitive system era. And the technologies that allow us to do that are basically these 4 fundamental categories of technologies. At the bottom, what I'm showing here are the device level innovations, which will give rise to about 1000x performance and or power reduction benefits relative to today. By the way, in this chart, the x-axis is time, and you can think about it somewhere about 10 to 15 years. So 1000x per 10 to 15 years, and whether it's 10 or 15 depends on the economic conditions and so on. That applies to all of the categories. After the device level, we're talking about the system level, where there are advances at the system level design. I'll briefly discuss that as well. That gives another 1000x. Then it gets very interesting at the application level, which is again the big data and big fast data, which is data at very low latency. That gives about 1,000,000x increase to the total amount of computational that is required. And then finally, I'll be talking about the programming algorithms and architecture, where we are going from the programmable system to a learning system or the cognitive system. So starting from the device level, so two fundamental ways that the device level enhancement will occur. One is the scaling, the lithography shrinking of the devices, which will continue for another few decades. And during that transition, there will be changes in the material as well as the various structures that will be used. And in addition to the scaling of the devices to make them smaller and lower power dissipation, there will be a three-dimensional integration of various functions. And one example of that is the 3D integration of photonics within a logic device. And this can also expand into, for example, integration of various forms of memory. For example, the phase change memory or other forms of non-volatile memory, together with the logic devices, all in the shape of a cube with a 3D structure, and the photonics for the very rapid and low latency I/O. The other form of integration can be a functional integration at the device level. So for example, what I'm showing here is a DNA transistor, where you have basically a narrow hole in the middle of a stack of insulators and conductors which are interdigitated, and then once the DNA is pulled through that, they can interrogate the DNA molecule and read the DNA very rapidly. That's an example of a functional integration where the computation can be done as the device is operating. The next set of advances will be at the system level. And it is very interesting that a lot of the progression that we have had in the high-performance computing, for example, the hybrid systems, for example, the highly parallel systems, are working their way into the commercial businesses, commercial systems for enterprises. And this will continue to evolve in that manner. And this gives rise to a significant system-level performance increase at lower and lower power dissipation. The key here is to integrate the total system stack. This starts at the silicon level and then goes to the packaging level, and then the various layers of the software, including the operating system, hypervisor, and then the middleware, and then it reaches all the way to the application. The way to think about this structure is that application is always the king, and based on that application, the rest of the system will be optimized to take care of that application requirements, both from the latency and computational power point of view. By doing so, the full system level integration and the optimization, we will reduce the total power reduction at a given performance by large factors, like what I mentioned, like 1000x. An example here, a set of machines that generated the 1 petaflop computing capability will go from a room size a few years ago to about a third of a rack size within a couple of years. That's a major dramatic shift on the performance enhancement at lower power. Now let me talk a little bit about the big data that I was referring to at the beginning of this conversation. So this chart illustrates both axes of the evolution of the data. The y-axis is the amount of data, as I mentioned, is growing exponentially both structured and unstructured data. Lots of it is unstructured real-time data that needs to be dealt with. And the x-axis here is the latency. And the further you go to the right, the latency is reduced. So it gets harder and harder from a computational point of view. You have less time to deal with a given data. So that's what we call big, fast data. The right-hand side of this chart explains some of the examples relative to the range of latency and the amount of data requirements that we have. And in order to deal with such a large amount of data, we basically need analytics to give insight on how to use the data. And you can think about the following, that data is basically an information on the past and the present, and analytics allows us to make better decisions about the future based on what has happened in the past. And also with the various simulation techniques, we can also predict some of the potential outcomes, and using the analytics decide which outcome is the best and how to achieve that. So that's the point of how the analytics work. Now, how they affect the system design, I'm showing in this chart. So starting all the way from the left-hand side of this chart is where we are talking about mainly structured data that the large SMP systems with fixed storage can deal with. And as we go more and more towards right-hand side, we are dealing with unstructured data that are generated real-time and need to be dealt with at low latency and as low latency as possible. Now, the system design will change as we go from the left to the right-hand side. For example, we will increase the amount of parallelization, the use of acceleration during storage. All of that is to increase the bandwidth and reduce the latency. And as we move to the right-hand side, we will get to the regime that not only you can do predictive analytics, but you can get very close to real-time predictive analytics in a way that most of the data that is being generated are now becoming useful. And this chart basically has significant impact on the way the computation is designed, how close is it to the data, and how the storage is working together with the computation to achieve that. So what I'm showing in this chart is basically the fundamental principle that in the next generation set of systems, we have to move the computation closer and closer to the source of information where the data is. So instead of having computational environment in one end and data in one end, and then bring the data to the computation and then give the result back to the various users, we have to bring the computation to where the data is. And that is what's shown in this chart. Going from the left to right, we are basically bringing the computation to where the data is. And the further we go to the right-hand side to get into the predictive real-time analytics, the more of that structure we have to create. And that includes the use of various storage class memories, various very, very fast I/O, and you'll see some of the aspects of the scaling of the systems that achieves this bringing the computation close to where the data is. On the architecture of the system, so I'm going to talk about, again, how do we go from the programmable environment to the cognitive or learning system environment. In the programmable era, which basically where we are at today, as I said, the computation is processor-centric and fixed calculation, and we move the data to where the computation is. Where we are going to, the computation will be data-centric, and statistical analytics will be the key to basically make use of that significant amount of data. And I'll talk briefly about the scaling concept for the system, which is very important to reduce the latency. So if you look at this system design that we have today, scale down is basically the shrinking of the components of the computational environment. And so the two fundamental ways that today we design the systems are scale out and scale up. So scale up is where you have a very tight connection between the processor and memory, and to the processor, all of the shared memory looks the same. That is very good for latency. However, it is not very power and cost efficient for large amount of data. Scale out is very good for large amount of data. However, the latency and the density is not very good because there is a distributed system, and then the latency of the interconnect and various components have to come in play as well. So the next phase that we have to get for this cognitive model is what we call scale in. And the simple principle of scale in is to get the benefits of both scale up and scale out into one system by bringing the computation and storage and I/O components as close together as possible. So basically what we do, we bring all these elements together. For example, the Pure system and the TISA systems are very good examples of this scaling at the system level. And then you bring all of that at a smaller form factor at a rack level or a board level. And then you go all the way to the component level, where a 3D cube of the computation and storage elements integrated together basically gives you the highly scalable parallelized system, as well as completely closed from an I/O interaction point of view. So the latency is very small, and at the same time it can scale. And that's a fundamental point of scaling. Now, going further in the cognitive direction, we are basically talking about various technologies that allow you to go next steps and away from von Neumann serial computational environment. So I'm going to talk about some aspects of the technology, architecture, and applications for this regime. An example of that is a SNAPSE experiment that we are doing, where we are basically modeling the computation after the way that a brain functions, where it has very large number of interconnects, but each computational element is relatively slow. And we have built experimental chips that model the way the brain functions, and we can see very interesting advantages in very large power reduction for aspects of computation such as pattern recognition, the way that the brain functions. Another example of non-von Neumann computing is the quantum computing, where in some aspect of computation such as cryptography, you can have very large improvements. So you can reduce the time of a computation, for example, for a factoring of a 3,000-digit number from several hundred years to several minutes. Now, at the moment there are limited class of computation and calculations that can use the quantum computing, but there are critical ones, including various aspects of the optimizations and also detection of various formulations for drugs and so on in pharmaceuticals that could be extremely beneficial. And this technology is at its infancy, but it has a tremendous it has a tremendous promise. So combining that fundamental building blocks of the technology with the set of architectures such as Watson. Watson is the machine that played the Jeopardy game in the US, which is basically a game of the question and answer. And then now we are expanding that from the architecture point of view, from a static question and answer machine based on text to an interactive, dynamic environment where Watson can interact with people on multimodal way through speech, vision, as well as text, and also have an iterative process of giving answers and then getting some feedback and creating new answers and various very powerful aspects of the machine learning that are involved in the next phases of Watson, for example, in medicine as well as the financial markets. As far as the applications, now the range is exploding, all the way from social businesses to the smarter cities and the sensor networks. And basically the underlying system architecture behind all of these are how do you deal with various forms of analytics that are operating on big data, and the system infrastructure underneath that can support that with very low latency for massive amounts of data. And in order to achieve these, I'm proud to say that IBM has been the patent leader for the past 20 years consecutively, with very impressive numbers, over 6,000 patents per year for the past couple of years. So I'm going to conclude my discussion, my presentation today by basically going back to this evolution of the computing, where we started basically from building fixed calculators to getting to programmable systems, and now we're talking at the beginning of the cognitive systems, where it gets very exciting, and it's a must to be able to deal with those huge amount of data at very low latency. Thank you very much, and have a wonderful day.